Welcome everyone to the first of a multiple part series on flotation modeling in HSC Chemistry version 9. So here we have a blank HSC sheet. In the simulation module we can add lots of different processes. However, we're going to deal with flotation. In this first video we're just going to have a look at what data is required to do the modeling, and then we're going to spend most of our time in Excel and look at the data that we actually have and how we interpret that data. I will refer you to the help section in either the main HSC or in HSC Sim. There's lots of very good tutorial videos on the Outotec YouTube channel. You should watch all of them on using the Sim module. The second thing is there's this thing called the help section. When you open help from HSC Sim, it tells you most of the things you need to know. So why am I doing this video? Because the manual is a bit light on a few subjects concerning flotation modeling from test work, and that's what we're going to focus on today. But just quickly, in the help manual you can read from section 40 onwards on the simulation common tools. We are going to be doing minerals processing, and there's a very good example in there as well to work through. The unit models are described in detail, and then we are going to be spending our time in the mass balance module and the model fit section. And you can see here, there we have flotation modeling, and a curve is fitted here graphically, but it describes the kinetics of flotation, and that will allow us to model from the test work what will happen in an operating plant under various conditions. So let's get started with Excel. I'm going to minimize this, minimize that, and let's go back to Excel. Let's have a look at the test work data we received from the laboratory. In this particular example, this was rougher flotation, and from the chemistry it looks like it was reverse flotation, so the silica was floated and the iron units were not floated, and a very clean concentrate was produced in the end containing mostly iron and very little silica. We also have other elements, so let's just have a look at them. From the calculated head going in, there's a bit of lime or calcium reported as lime. There's a bit of magnesium reported as MgO. There's very little phosphorus. There's very little alumina. There's a little bit of sulfur going in. There's very little titania going in. A little bit of chlorides. The LOI is minus 2.5, so that tells us that it wasn't pure magnetite going in, and something added some positive LOI, which could be carbonates, CaCO3, MgCO3, or perhaps some goethite, or some other things with combined water or combined carbon units. Okay, so this is the data we have. We completed this flotation in 8 steps. So in HSC simulation module, we need to create 8 flotation units with a concentrate stream going off every minute, and then we had a feed going in, and we have a rougher tail coming out or remaining in the test reactor at the very end. We are dealing with MTS H sample or site test work number 9. The important here is the H suffix. This is the H material type. The second thing we need to look at is, what does the sample look like? So the laboratory received the sample. It was minus 3 millimeters, had 31% Fe, lots of silica, very little alumina, a little bit of lime. We've gone through this, a little bit of sulfur. This one says 0.2 sulfur. So that is interesting. So the laboratory did two types of mineral assessment. They did an XRD and they also did some QuemScan data. Let's have a look at both, because this will all make sense once you understand what we need to do and how this all fits together. Starting with the XRD, it says that in all the samples analyzed, remember we're just looking at the H, which is actually not even on here, but there was a lot of quartz. There was a lot of spinel group, which AB204, and A could be the same as B, so Fe.Fe204 or Fe304 in our case. Chlorite, very little. We're going to ignore chlorites. Talc, 8 to 22%. Now remember, talc, it has magnesium and silicon in, together with some OH ions, which means, or combined water, which means that we can actually add a positive LOI from talc. Dolomite, there's some dolomite, 5 to 8%. There's very little calcite. So dolomite being AbCO3, where it's the A could be calcium and the B is magnesium, whereas in the calcite group it is just A2 plus. In other words, that's like CaCO3, so it's a pure form, not a mixed form. Pyrite, less than 1%, but this could be where our sulfur comes from. And then there are amphiboles, so what I would call junk minerals. It's a mixture of various different things. Could be some sepiolite and some amphibole, in which case we don't really know what's in it, but we do know that they could have OH, fluoride, chlorine, etc. in anything between 1 and 9%. When we get to sample H, we'll have a look at that again. So this is one analysis that says it's predominantly quartz and magnetite slash spinel group. Now, when we look at hematite, this one says there's less than 2% hematite. So in our simplistic example we're going to do today, we can actually ignore the hematite. But this is only from the XRD report. As you know, you have to tell the XRD machine what minerals are present and then do the analysis. It doesn't know because it has a plethora of minerals to choose from. So if you choose wrong at the start, well, you're going to get the wrong answer. So let's have a look at the QuemScan images and then the QuemScan results, and then we look at what it tells us in the end. So here we go, sample H. Let's make this a bit larger because it will be quite insightful. 150%. Let's have a look. So the legend says grey is magnetite, burgundy is hematite, brown is oxides slash hydroxides of iron. There's some Fe sulfides, let's call it pyrite for now, and quartz is this pinkish color, and there are some silicates in green, and it's supposed to be some carbonates and others black. Now find me the carbonates, the blue color. Can you see any? I can't see any. That's an important thing. So if we look at magnetite and hematite, it says that they are very small and they're mixed intimately together. So we can consider them as one mineral. But from these results, it looks like there's in some particles more magnetite and other particles a bit more hematite. On average, using my eyeball statistics, let's call them 50-50. But we'll get back to the split of magnetite hematite because that's important. So QuemScan tells us what the mineral abundance is according to itself. And here we go for sample H, which is this bottom one. We have magnetite, just over 20%, some hematite, just less than 20%, some other iron oxides slash hydroxides like goethite, Fe sulfides, let's call that pyrite, a little bit of carbonate, we didn't even see it in the sample, quartz, and some other silicates, and a little bit of other. The next tab in this worksheet is called Data Validation, and it's quite insightful. Let's have a look at the QuemScan data validation, and then we'll do the XRD data validation as well. Starting with QuemScan. Remember that it concerns chemical elements, not oxides or sulfides or anything. So we have to revert to calling it aluminium. So the QuemScan aluminium for sample H, yes, that looks good. Calcium 0.9, 1.3 between the QuemScan and the chemical analysis of the head, that's good. Fe 35 to 31%, slightly off, but you know what, it's in the range of 30 to 35%. I'm going to accept that. Magnesium 1 to 1.7%, slightly off. Silicon 21 versus 24%, you know, slightly off, but not bad. Interestingly enough, some of the other samples, the differences were more marked, where you know we have 10 versus 14%, 47 versus 40% for Fe, etc. The XRD reconciliation for not for sample H, as you can see, it's not there, but for the other samples, they are certainly a lot more consistent, and there are no differences. So we don't have XRD for sample H, but we're going to just go with the mineral list that we have. Speaking of mineral list, just as a reminder, we have magnetite, hematite, goethite, Fe sulfides, carbonates, quartz, silicates, and others. We'll get back to this one shortly. Back to the first workbook. We had 8 minutes of flotation time. We had a head assay and we had a tail assay, and all the concentrate streams that we've drawn off after 1 minute intervals. In the next video, we're going to construct a simple flow sheet in HSC simulation module. We're going to enter the data, and then in the videos after that, we're going to do the mass balancing. We're going to do the model fit so we can calculate the kinetics of flotation for each different mineral, and then we're going to model an actual operating plant. So let's do this in 5 videos.